Hello. Uh, I see Rohi joining in. Let me admit him. I can share my screen. Mm, share. Yeah. Okay.
Hello.
Hi Rohi. We'll wait for 1 minute. We'll see if anyone else is going to join. Else we'll start. Yeah.
Okay.
Okay. In the meanwhile, Rohi, I just completed uploading all of 27 days of the materials which we have related to the introduction to Python programming. That's already updated into our LMS, but the only problem is that with section day 4, I have lost the video or the video recording for a day 4. So that is lost. That is unfortunate. I don't have a copy of that. I hope everybody has taken notes because I've unfortunately lost that because that is when uh, I had that issue uh,
Mm,
with. Uh,
okay. Okay. No worries. Yeah.
do you have a copy of that with you? I don't see that in my sent items. I don't think I have sent it on mail as well.
I will have to check if
Okay.
you have said. Yeah.
Okay. If you find it, do let me know because I'm not able to find that in the sent items. I'm under the assumption I've not saved it and I've not sent it. And on the same day, I had that problem with GoToWebinar. So that's why things got messed up. Hi, Sarang. Okay. Let's give it a start then. If anyone else is going to join, they'll join. So I hope you can see my screen. So we quickly discussed yesterday, last day on the types of probability. We looked into classical or a priori probability, which is like the textbook way of taking a small sample or doing a single experiment and then trying to find out the probability. Then we looked into empirical probability. This is more like data-driven approach. So this is where we usually gather proper data using proper sampling technique, and then we apply the rules of, let's say, probability. Then we looked into subjective probability. This is applicable in industry in case where I don't have any data from any of my past experience because there is no past experience. Then we looked into types of events. We looked into mutually exclusive events. We looked into independent events. We looked into disjoint event, and we looked into non-disjoint event. I'll send you a small website, a link. I'll maybe as of now I will be sending mails only because I've not completed updating my uh, the LMS portal, but I'm sure it will be done by Yuri today. Another one after this class, if I put another half an hour of effort, it will be done. So I'll start uploading everything into the LMS. I'll be sharing the documentations there as well. So I would strongly recommend that you go through them from where we can continue because then these are the basics basis which we will be doing a lot of, let's say, machine learning. So please don't be under this impression that we are learning this just to know about, let's say, probability. It's not. When we learn these, and if we learn these well, then there will be some machine learning algorithms which are specifically probabilistic, which will be very easy for us to understand. Or otherwise, they'll remain a black box. And then we'll only be importing a library into Python or R, and then we will be using them. But tomorrow, if they fail, or if I want to improve them, I won't be able to do anything. Right. So that's what the meaning of these are. So we are not trying to revise whatever we have learned in school. We are trying to revise them because we would like to know how a data analysis technique is going to work. That is the reason why we are doing this. Right. So let's continue from there. So we will continue with the rules. So we started with the rules, but we could not complete the rules. Right. So that's from where we are going to start. So we are going to start with the basic rule, which is known as, let me just write rules of, 1 minute, just a moment. Yeah, rules of probability. Okay, so the first rule of probability that applies, and this applies specifically to mutually exclusive events. So applies. Uh, so this I can't say it applies directly to mutually exclusive events because it's quite tricky to get this done by a mutually exclusive event, because that is what we saw in the last class as well. But what is the rule is that if I have two events A and B, okay, I have two events. I have a set of two events A and B, and I will assume that these two events are going to simultaneously occur. So it means that usually, or I will assume that A or B are mutually exclusive. Okay, so sorry, they are not mutually exclusive. So because they are not mutually exclusive, they cannot simultaneously occur. If they can simultaneously occur, then this rule will not be applicable. We'll have to do something else. So this is for events like A and B, where A can be anything, B can be something else, which do not occur simultaneously. Okay, so if A occurs, B cannot occur. So if that is the case, then A and B are known as mutually exclusive. If that is the case, then we will not be able to use the addition rule. In some cases, we can tweak that as well. Yeah, we can try to do experiments in a certain way that multiple experiments are being done at the same time, and because of that, maybe we will be able to tweak that. But that's not really the right thing to do, because that is like imposing or removal of a constraint, right? So that's not what we do. Usually, what we do is there are two events A and B, and the probability of getting the both of the events together, because mutually exclusive events, if A and B are, then they cannot occur simultaneously, in which case this rule doesn't apply to them directly. But if there are events which can occur directly, then we say that the probability of A, and this is going to be really interesting because I'm going to write this like this, but please read this U as something else. So maybe I'm going to write it like this. Okay, so P of A union B is simply considered as probability of A plus the probability of B, where probability of A is the chance of occurring of, or the chance of occurrence of event A, and probability of B is the chance of occurrence of event B. So if I need to know what is the probability of A and B occurring together, which is seldom the case when it comes to mutually exclusive events, then I'm going to use the addition rule. Now, what happens when events are not mutually exclusive? So this is something which we have already covered yesterday, okay, or in the last class. Now what we are going to look into is case where A and B are not mutually exclusive. If that is the case, then we are going to use a rule which is known as multiplication rule. Okay, so multiplication rule is applicable specifically when events are A and B, and I must have written it over here. A and B events are uh, addition rule. Okay, so just a moment. A and B not uh, mutually exclusive. Okay, so these are non-mutually exclusive events, because A and B, if they are mutually exclusive, they cannot occur simultaneously, right? So, but this rule applies to mutually exclusive events as well in some cases, as I said. Now I have events A and B, and A and B are uh, uh, not mutually exclusive. Okay, or they can be mutually exclusive as well. Okay, but then in this case, what is going to happen is, let's say I'm going to take an example so that I can explain. This will sound confusing at the first place, right? The rules are applicable both on mutually exclusive as well as non-exclusive kind of thing, but when you understand the scenario, they will be clear. Okay, different textbooks are going to represent them into different formats, but ideal condition addition rule, they apply onto the cases where things do not occur simultaneously, and multiplication rule occurs when they can occur simultaneously. But I have actually written in the opposite way, right? So not should be over here. The reason why I have written it in the opposite way is because this formula that you see over here is equally applicable for mutually exclusive events as well as not mutually ones, because I can create such a scenario by doing the experiment at the same time. So if I'm doing an experiment to calculate probability of A and probability of B at the same time, okay, let's say I have a machine, I have two machines to roll dices. In that case, if two dices are rolled at the same time, probability of getting A or probability of getting a 3 and probability of getting a 5, which cannot occur from the same dice, right? So this is one dice, this is, let's say, dice 1, and I'm rolling dice 1 using a machine, and then I have another dice which is dice 2. Okay, so I'm rolling dice 2 using another machine. Okay, so machine 1 has a roll dice 1 and machine 1 has a roll dice 2, or maybe I have two hands, right? So why not? I'll roll the dice 1 with my left hand and roll dice 2 with my right hand. So at the same time, I'm actually doing two experiments. Then in dice 1, I'm interested to know whether I get a 3, and in dice 2, maybe Sarangs is interested to know whether he gets a 4. So if these two events are going to be done at the same place, two experiments are being done at the same place, then the probability of these two events is 3 by 6 and 5 by 6. So probability of getting a 3 out of 6 possible outcomes is 3 by 6. The probability of getting 4 out of 6 possible outcomes is 4 by 6. So the occurrence of 4 is 1, occurrence of 3 is 1, right? So when I calculate the probability, this 3 out of 6 combinations becomes 1 by 6, right? That is what we have already seen in the probability rule. So I have an event which is occurring or which is going to occur only once out of 6 possible events. So the probability is 1 by 6. Then I have another event, part of a different experiment done at the same time, whose probability is also 1 by 6. So total, I take a total and I simply say it is 2 by 6 are also equal to 1 by 3. So 1 by 3 is the probability of A union probability of B. At the same time, if I'm doing two experiments, this is going to be the case. Okay, this is the reason why I am writing it in this way, because it works for both the cases, right? But let's not try to confuse you. You will anyways be confused when you apply the probability. This is a bit confusing at the start. Over a period of time, it's going to work well. Now, let's look into multiplication rule. So multiplication rule is a very interesting rule, and this can be somehow explained by means of 3D diagram. So let's say I have a set which is something like this. This is going to be a very bad diagram. Okay, this is really going to be a very bad diagram. So imagine you are in a 3D space, and this is a space. Okay, and this is also a space. Okay, this is a space in 3 domains. So you have y-axis, you have x-axis, and you have z-axis. Okay, the x, y, z, there are 3 axes, and you have this hyperplane, or this plane which is P1, and this plane which is P2. Okay, so you have two planes over here, and somehow you can see that one plane is just above the other plane. There is an intersecting area. Okay, there is an overlap of area. Okay, which is this much. This much area is actually getting overlapped, right? So this much area I can say is actually an overlap between these two, because P2 is standing over P1 and P2 is guarding or blocking this much area. Why did I take this example? Is because, let's say, the example which I think I started taking in the last class, but we could not finish. Let's say I have a bag and I have 3 kinds of balls in there. So one kind of ball is a red ball. One kind of ball is where there are, let's say, cricket balls. Okay, so cricket ball will have a grip like this. We know that already. Okay, and then there are other balls which are like custom made balls. This has come from some other country, and they have this kind of cross lines and they have this cricket line as well. So they have a hold like you see in the cricket ball, and then they also have crossed lines. So these are like crossed lines, these are like single lines, and these are red lines. Okay, these are simply red balls. So what is the probability that I pick up a red ball and that ball is also a cricket ball, or it does also have a single line, in which case there is clearly an overlap, right? So if I consider this P1 over here, if I consider this P1 as a set of all the R balls, and I consider this plane P2 as the set of all the SL balls or single line balls or cricket balls, then there will be some kind of an overlap, right? Because there will be red colored balls as well, which are used into cricket and which will be of this kind of a shape, of this kind of a format, right? So this is the intersecting area. Don't worry, we are going to take a better example as well with cards, and then it will be clear. So multiplication rule is applicable when this kind of an overlap is there, which means they are events which are not mutually exclusive, which means ideal condition they are overlapping with each other. There are events which will have this kind of an overlapping section, right? The one that I have actually drawn in red over here. This overlapping section will be there, kind of a shadow section will be there. In this case, what I have to do is that I need to take the probability of both events A and B. So let's say event A is that of the red ball and event B is that the ball is also a straight line ball, right? Then I have an overlapping area. So this overlapping area is something like this. It covers some part of this hyperplane P1 and this plane P2, right? If I take a probability and simply do a plus, which I did in the addition rule, which also I'm going to do in the multiplication rule as well. Okay, so multiplication rule is just an extension of the addition rule. How did this come into picture is as simple as this. In mathematics, multiplication is actually an extension of addition. Okay, so if you are going to say, let's say 3 multiplied by 2, what is the meaning of 3 multiplied by 2? 3 multiplied by 2 is 3 plus 3. You simply are adding 3 two times. So if you add the first variant this times, or if you add the second variant this time, you will get the same number. So 3 multiplied by 2 is basically, or it can be very simply represented as 3 plus 3. Or you can represent 3 multiplied by 2 as 2 plus 2 plus 2. In both the cases, you see, I have actually converted the multiplication into the addition operators. So simply that applies here as well. Multiplication rule in this case is just an extension of the addition rule. But if I do the addition of probability of A and probability of B, so this set's probability will be calculated and this set's probability will be calculated. If I add both of them, this section will be added twice, right? So I am adding a section which is this one. This is section S1. This is section S2. Section S2 is on top of S1. It is superimposing S2. And then if I'm going to calculate the total probability of this one, say, let's say PR1 and then PR2, okay, very bad drawing. Then PR1 and PR2 is going to take this S1 as S12 as well. And then the probability will be counted 2 times. So that is the reason why I at least have to get rid of one overlap over here. You see, there are two sections. One is the bottom section of this plane P2 and one is the forward section or the upper section of this plane P1. So I need to get rid of at least one. Why not I get rid of one? Okay, so if I get rid of this one, the upper section of the plane P2, okay, then obviously I am getting the right results because now I have this area, this overlap area, and this extra area. So this extra area, and one of the overlap area. So that addition or that calculation is going to be correct. That is the basis of doing the multiplication rule. So in multiplication rule, what I'm going to say, I'm simply going to take this and simply going to paste it over here. This is the multiplication rule with just a small change that I'm going to do. Very, very small change. I'm just going to do a minus. Okay, I'm going to do a minus of A, and this is really going to be tricky. I don't know how I'm going to do this. Intersection, there is no symbol on my keyboard in which I can do ulta U. So this is like the inverse of U. So I'll just say intersection. Okay, so A intersection of B. So this is mathematically represented something like this. P of A intersection of B. Okay, so this is a set notation sign. This is intersection sign because this intersection sign is what I have written as INT. But then this P of A union B, union U is something like this. You draw it a bit more bigger than a regular U. So this becomes this one. Okay, so this is this U sign that I have. U was there in the keyboard, so that was easy. Right, so that's the formula here. This is known as the multiplication rule. It's a very, very simple rule, very common rule. This rule says probability of the union of A and B is determined by adding the probability of event A, which was getting a red ball, and then B, which was getting a ball which has a grip like a cricket ball, and then subtracting the probability of the intersection of the events A and B. Because if I don't do the subtraction, there is going to be, let's say, double counting. Right, I have to subtract at least one of the intersection points, right? So let's say I can take an example. Okay, let's try to take some examples and we can see how it's going to go. Okay, let's start with the addition rule. Okay, we'll take some example of the addition rule, and we can say this is an exercise, okay, or a question that we are trying to solve. So a question for addition rule is that, let's say I have a pack of well shuffled cards. Okay, I have a deck of cards. A deck of card contains 52 cards. There are 4 colors in the deck of 52 cards. There are 4 types of, let's say, shapes. So I have 13 shapes or colors of each and every uh, type, right? So I have, let's say, spades, I have diamonds, and so on. So there are 52 card case, or a pack of 52 card, and I have that well shuffled. Okay, and then the card is picked at random. Please note that statement, because we are going to change this statement later on. From a pack of well shuffled cards, a card is picked at random. Okay, so I have a well shuffled pack of 52 cards. I pick a card from this set, okay, at random. Okay, so there is no specific way in which I have selected. Then I would like to calculate the answer of 2 questions. So question number 1, I have, what is the probability of the card, okay, the selected card maybe, or the drawn card being uh, a king or a queen? Okay, what is the probability that the card that I have drawn is a king or a queen? Okay, and then I have a second question, which is, what is the probability that the card is a king or a diamond? Okay, I should not have written this over here, so let me just cut this over here and let me paste it below, because I'm going to tell you why I did this. Is because these 2 questions that I'm going to answer, the first one will be solved using the addition rule, the second one will be solved using the multiplication rule. I'll tell you why. The first one is a probability of a king or a queen. Okay, in this case, these are completely mutually exclusive events, although I can do the experiment in parallel. But these are completely mutually exclusive events, in which case, when I draw a king, because I am drawing only one card, okay, I pick one card, okay, one card. Okay, if I am picking only one card, it can either be a king or either be a queen. This is one experiment. Okay, so I am doing only a single experiment here in this example. Okay, then I'm drawing one single card in one single experiment. I want to know whether it is a king or whether it is a queen. Okay. Now, how do we solve this problem using the addition rule? How many kings are there in my card? Okay. So the solution for, let's say, 1. Okay. How many kings are there? Kings in my card set is 4. Okay. How many queens are there? Queens in my card set is 4. Okay. I have 4 kings. I have 4 queens, because I have 4 types of cards in the deck of 52. For each and every type, I have 1 king. I have 1 queen. Okay, then if I say, let's say A is the event of getting a king and B is the event of getting a queen. Okay, so I have simply defined it so that I can apply that math, right? So if I am going to calculate the probability of what, A union B, I need to calculate. Addition rule is going to be applied over here. King or a queen union, either of this or this. If this was AND, I would have taken an intersection. Okay, union refers to the word OR, right? This is not equivalent to any kind of, let's say, electronics theory that we may have read into college. This is actually different. This is basis the statistical theory. Statistical theory says this union letter that I have, or set theory representation of union, says that it is representative of OR, and it is not a representative of AND. So union does not mean AND in this case. It means OR. This is an event and this is one more event. What is the probability of getting OR? Then I solve it like this. So probability of getting A or B is probability of A and probability of B. So what is the probability of A? I have 52 cards, so I simply say 4 by 52. Right, for a king. So probability of A is 4 kings I can have out of a deck of 52. Probability of B is what? Is also the same thing, right? 4 divided by 52. I have done a typo, let me correct that. Right, so if I do a probability of A plus B, this is 4 by 52 by 4 by 52 is equal to 8 by 52. Right, if you do a math, this 8 by 52 is come as 2 by 13. Okay, So this is the case. Because this 2 by 13 is like 4 by 26 and then 2 by 13. Okay. So this is where you apply the addition rule. Addition rule is applied in case you have mutually exclusive events usually. Okay. One cannot occur if the other is occurring. Now, what is the solution for the second one? Second one is going to be tricky. Why? Because I have a deck of 52 cards, out of which there are 4 kings and there are 13 diamonds. Okay. So how many kings are there? 4. I have diamonds, which is equal to 13. Okay, I have 13 diamonds, I have 4 kings. So let's say again, I'm going to take this over here. Let me copy paste and let me say A is the event of getting a king, and B is the event of getting a diamond. Okay, if that is the case, let A is the getting a king and B is getting a diamond. The two events here are not mutually exclusive because you can have at least one card which is both king and a diamond, which is known as the king of diamonds. Right, so that is how you identify from the question. You identify that this is what the case is, right? So how do you find that out now? You have to do this. You have to do this. Okay, so what do you do in this case? Okay, let me just do it in this way. So what is the probability of A getting a king? So this is very simple. Probability of A is getting a king. Getting a king is 4 divided by 52. Simple. Right, what is the probability of getting a diamond? So what is the probability of B? This is 13 by 52. Right, I have 13 diamonds and I have 52 cards. Right, if I put this into this formula, what is going to happen? Right, what is the probability of A intersection B? Okay, or A intersection B. Let me calculate that as well. How many cards are there which is going to be king as well as a diamond? 1. Right, so 1 out of 52 card is going to be such a case which is a king as well as a diamond, right? Because that is the king of diamonds. So how do I solve this? 4 by 52 plus 13 by 52 minus 1 by 52. Okay, so clearly I have 13 minus 1, 12 plus 4, that is equal to 16 by 52. Right, so this is the probability. So if I try to denote this, this will be something like 4 divided by 30. Right, so this is how I can calculate, or I can try to solve these kind of questions. So these kind of questions are where you need to read the questions very carefully. If you read the question carefully, you will come to know what kind of a problem that is, and accordingly you simply apply a formula. Right, let's take a quick break. Is there any question from anybody?
No.
No, Bhamik.
Okay, then let's continue. Okay, then let's look into now the actual multiplication rule. So what I said over here is not really a multiplication rule. Okay, this is a multiplication rule which is extension of addition rule. Okay, so this is not really called a multiplication rule. This rule in textbooks you will find them as addition rule only. Okay, so how do you differentiate? You simply write this. Okay, so this is the ideal condition when events are mutually exclusive. This is the ideal condition where events are not mutually exclusive. That's all. Okay, but there is even a more formal multiplication rule. Let me just define it over here and then we can continue. More formal or maybe I can say practical, where multiplication is equal to multiplication, not represented as addition, is the multiplication rule, where you simply have two events, event A and B. Okay, now these two events are what? You have two events if those two events are independent. So we have already seen are independent. Okay, we have seen what are independent events, right? They are independent of each other. Okay, these are not disjoint. In the last class we had a question, right? So independent events may or may not be disjoint events. Okay, but these are independent of each other. A does not impact B, B does not impact A. The probability of simultaneous occurrence of event A and B, where A and B are independent events, is also known as the probability of intersection of A and B, right? So that is known as the probability of intersection. Okay, so it is clearly as simple as this: A and B occurring together. A and B events are occurring together. Okay, why they can occur together? Because they can occur simultaneously. Since they can occur simultaneously, I think the spelling is right. Yeah, they can occur simultaneously because they are independent of each other. I can do this with n number of experiments as well. Like there can be more than 2 events as well. So there can be n number of events, n number of experiments, n number of trials which I'm doing, and these 2 events or n number of events are independent of each other. In which case the rule simply says that I have this intersection of A and B, which are A and B events which are occurring together, and then mathematically I simply say probability of A multiplied by probability of B. Okay, so if I take the probability of 2 independent events and try to multiply them, it is as simple as that, right? So let's take an example and then let's see how this goes. The example is going to be, let's say, from the education side. So let's say the probability that you will get an A grade into quant or any subject, let's say statistics. Okay, so you are giving an exam and okay, we have only 10 minutes left, so maybe we'll have to move a little bit fast. Let's see if we can extend the multiplication rule. Okay, so the example is that you have given an exam of statistics. You have also given an exam of, let's say, linear algebra. Now, statistics and linear algebra may be interlinked when you are doing the data science related activities, right? But in themselves, there are many few concepts of statistics which are borrowed by linear algebra and vice versa. So they are exactly independent events or independent areas. And then you giving an exam of statistics and you giving an exam of, let's say, linear algebra, maybe on 2 different days, 2 different textbooks, 2 different teachers who have taught you, 2 different rooms in which you are sitting. Maybe the people sitting around you are going to be different as well, or maybe they are different. It's going to be 2 independent events because these 2 courses are independent, right? So let's say that the probability of you getting a grade. So I'll just say this is an example. Okay, so yeah, probability of, let's say, A. Oh, okay, no, first I should be defining the events. Events are A is grade in stats and B is the grade in linear algebra, right? So I have stats, I have linear algebra. I've already proven these are independent events. The probability of you getting an A in stats, okay, grade A in stats. Okay, these are my events. So I'll just write this. Grade A means you have scored really well. Okay, so the probability of you getting a grade A in stats is probability of event A, which, let's say you have done some experiment, you have found out it is 0.7. And then you have the probability of event B, which you have also found out, which is equal to, let's say, 0.5. Okay, because these are independent events, okay, then in this case, the probability of intersection, right, that you are getting a grade, or maybe I can simply copy this first and then I can say you getting A in both subjects. Okay, you are getting an A in both the subjects. So this is an intersection. This is an intersection because these are 2 independent events, which is then going to be defined as the probability of A, which is 0.7, and then the probability of B, which is 0.3. Sorry, 0.5. And then this will be equal to 0.35. Why is this the case? Because the occurrence of this number does not affect the occurrence of this number. So we have to find the intersection, right? So what we are trying to do over here is that I have an event which is this. I have an event which is this. No, this is a bad diagram. This is a very bad diagram. So this is one event which is my grade A in stats, right? And let's say I have another event which is grade A. Yes, this one is good diagram. A in linear algebra. I am here to figure out what is the probability here, right? I am getting a grade A in both, right? What is the probability of I getting a grade A in both? So that is why I want to figure out the intersection. So I don't have to plus this area and this area. I don't have to take a sum of the area of this block and then do a minus, right? I simply need to take the minus because I need to take this area, the area that I have highlighted in orange. I need to take this intersection area. That is the reason why what I'm doing, I'm simply taking the probability, multiplying them, and that is going to give me the overlap, right? So this is how we define the multiplication rule on one part of multiplication rule, or I'm going to say this is one part. Okay, so this is just one part of what we have done. Then there is one more part. Let's quickly see that and let's see if we are able to finish that. So these examples will be changed. Okay, don't worry. There are other cases. There will obviously be other cases where the events are not independent. Then what will you do? Okay, what will be an example? Let's say you are drawing again a pack of cards. Very simple thing to take example. From a pack of cards, you are drawing two cards this time. Okay, one after the other. So you have a pack of cards. You are drawing two cards. After every draw, you are not replacing the card back, right? You are not going to put the card back. Let's say I have 52 cards. I have picked one card. How many is left? 51. I have picked one more card. How many is left? 50. I'm not putting that first card back and then selecting the other one. Now the question is, what is the probability that in both of these draws you will get a spades? Okay, this is a problem where the events are not independent. Okay, and this is where conditional probability will be used. So when you have a problem where conditional probability is in use, it's almost always the case that non-independence of events is forced by something which I should write over here. Okay, I should write over here, not independent. Let me just remove all these things. Okay, and I'm going to write non-independence is because of a feature or a factor or a specific which you can call, how can I define this? It is known as non-replacement method. I'll not call it a technique, non-replacement method of sampling. Okay, so this I can take, and this is I can try to compare with this one. Okay, where is my example of this? Yes, I was picking a card, a king or a queen. In this case, I pick one card from this set. Okay, in this case, I'm going to, in each and every experiment, pick one card from the set, then I'm going to put it back, right? So if I'm going to put it back, my sample every time is going to be that of 52 cards. But in this case of an example where, let's say, I am draw two cards from a deck of 52 cards. Okay, do not put the first card back before pulling the second card. Okay, if this is the case, what I'm doing is after the first card is picked, my sample size is reduced, right? So this is kind of a non-replacement, let's say, method of the sampling. This is not a sampling technique, by the way. Okay, this is just a fancy way to represent what can cause independence or non-independence. I'm sorry, in this case. So in this case, what are you going to do? This is going to be tricky. Okay, let's say I have drawn two cards. Okay, so my question is clearly, what is the probability that in both the draws you will get a spade? Probability that both time I get a spade, right? If I'm going to do this, then what is going to be the answer? This answer is not going to be simple. So let me define the function first, and then I'm going to do the probability of getting A. Okay, probability. Sorry, I should write this as question, otherwise you will get confused. Okay, this is a question, this is an answer. Okay, now the probability, maybe we'll have to stop in the between the example. Okay, because I have only 2 minutes left. So let's see how much we can do. Probability of event A. How many spades are there? There are 13. Okay, so probability of event A in this case is going to be 13 divided by 52. Simple. The probability of getting a spade is going to be 13 divided by 52. Anybody could have answered that question. Okay. What is the probability of getting the second spade? This is going to be 13 out of 51 because now you have one card less. You have already picked up the first card and you have not replaced it. Right? So how do you do that? How do you do the calculation now? The multiplication rule says you have to take the diagrammatic representation also, which we have seen. We have seen that we are going to simply take the multiplication. Then if I'm going to take the multiplication, what is going to happen? In this case, this is going to be 13 divided by 52 multiplied by 13 divided by 51. Right? Is that really the case? The answer is no.
Bhawmik, it should be 12 by 51, right?
Yes, yes. It will be 12 by 51 here because I have already taken one card. Right?
Yep.
So it will be 13 by 52 multiplied by 12 by 51. So if I do a calculation, roughly this will come as 1 by 70. Right? So this rule is where I am doing an interface, or maybe we have very less time. Let's stop here. We will be continuing tomorrow. We will be continuing from the same example. Okay. Thank you.
Thanks, Bhawmik.
Thank you so much.
Thank you.
Good night.